let's look at some questions involving phase change and specific latent heat. And we'll start off, as ever, with a multiple choice question taken from a paper 1 standard level. Boiling water is heated in a 2 kilowatt electric kettle. The initial mass of water is 0.4 kilograms. Assume the specific latent heat of vaporization of water is 2 megajoules per kilogram. What is the time taken for all of the water to vaporize? So, what do we know? We know Q equals ml. We know m is 0.4 and we know L is, it says, 2 megajoules. So we'll convert 2 megajoules to 2 million joules, 2 times 10 to the 6 joules, and we get a value for Q of 8 times 10 to the 5 joules. 2 times 10 to the 6 joules per kilogram multiplied by 0.4 kilograms. 8 times 10 to the 5 joules. We know that's the total amount of energy we need to produce. Energy equals power multiplied by time, another equation that you need to know. So 8 times 10 to the 5 joules equals 2 times 10 to the 3, which is the power, 2000 watts, multiplied by T. Rearrange for T and you'll get T equals 400 seconds, so B is the correct answer. Moving on, we'll look at a more involved standard level paper. Now, if you watched my previous video where we looked at the physics here, I promised you that we would, one of the examples, one of the questions would be looking more at the experimental determination for the latent heat of fusion in this case, and here we go. So you're dropping an ice cube into the water in a well insulated calorimeter of negligible SHC. So the calorimeter itself we don't need to worry about in our nice simplified physics world type question. So the mass of the ice cube is 25 grams, the water it's going into is 350 grams. The ice cube, as I said, would be useful in my early video. It's 0 degrees C, so we don't have to worry about the specific heat capacity of the ice and heating up the ice. All the ice will do is melt. It will melt and it will then mix with the already existing water until the entire thing is at an equilibrium temperature, as it says, of 12 degrees C. So the initial temperature of water was 18 degrees C. It's going to lose energy. And the amount of energy it's going to lose is going to be whatever energy it needs to cool down from 18 degrees C to 12 degrees C, so 6 degrees C. So Q equals mc delta T, where m is the mass of water, C is the specific heat capacity of water, and delta T is 18 minus 12, so 6 degrees C. That's the water lost, the energy lost, and the energy gained, you know, balancing out. Will be the energy required to melt the ice, so ml, and energy required to warm the ice up, so m ice. C, I've put C ice there, which I shouldn't have done actually because it's just water now at this point, delta T. So 0.350 times 4,200 times the change in temperature on one hand side, 0.25 grams times L, the unknown, plus 0.025 times 4,200 again, specific capacity of water, times 12 because it's going from 0 to 12 degrees. Work that all out, you get 8,820 equals 0.025 times L plus 1,260 joules, so 7,560 equals 0.025 L. So therefore L equals 302,400 joules. Now you might, I guess, have remembered the specific heat capacity, the specific latent heat of fusion of ice. That was a number that actually featured in the last video, and guess what? It's not exactly 302,400. It never is going to be the book value if you have to work it out, because they don't want you remembering it and then just writing it down. Okay. At the same time, it's never going to be that far away. So if you remembered that it's about 330 or whatever kilojoules, then well done, good memory. Okay. and that will help you test whether your answer makes sense or not, but it's never going to be that answer exactly. Okay, thank you very much.